Radar was pioneered in World War II by Sir Robert Watson Watt to give the Allies an advantage. It was revolutionary because radar is capable of seeing through clouds and other obstacles, whereas planes at the time could not. However, as with anything, there are always limits, and with radar, the issue is that the antennas could not be long enough to produce high-quality images, and thus synthetic aperture radar was invented. Synthetic aperture is basically a technique that makes up for a shorter antenna by taking more pictures.
Synthetic aperture radar works by accumulating data on a small region of interest through thousands of scans. Once this data is gathered, it is run through the back projection algorithm, which gives the signal amplitude for each pixel at every scan. This is done by calculating the Euclidean distance, or the range, from the aircraft to all pixels. Then, every pulse data is aligned so that the original amplitude at each pixel arrives at the same time for all pulses. This is repeated for every scan. The amplitudes are then integrated and graphed. Our first implementation used a chain of nested loops to loop through each pixel and scan, which worked but was very inefficient. Not to mention we had several errors that yielded us images that made little to no sense. And after hours of debugging and looking over our code, we were able to solve these issues. Then it was time to make the algorithm run more efficiently through interpolation, which sped up the projection time considerably. After many different implementations, our team was able to make the final code 300 to 400 times more efficient. We learned that by using multi-threading, NumPy, and other well-implemented Python libraries, we could vastly cut down the time.
The next step was creating a radar interface to talk to the emulator. There was a very specific format our messages had to follow, and this was found in the API guide. First, we established that communications worked, and then we set the configuration of each setting. After that, our code asked for command of the radar, and then for information from the scans. We did most of this coding in a live share where we were all working simultaneously, and things were mostly going well. After testing the code, however, we realized a few problems. First, that we couldn't accurately track how many times a step was being retried before the code quit. Then, we had to solve for bit failures. After all of that, though, we were successful in creating a working radar interface.
To make this radar interface more easily accessible to the operators, we then started on creating a website GUI. We quickly built the website, but then realized that connecting HTML code to Python code was not easy. We started researching Django and Ajax, but nothing we could find seemed to work.
Eventually, we decided to focus on collecting the data from the website and then sending it to the radar. This turned out to be complicated because the server we were hosting the code on would not print anything in the console. After tweaking settings for hours, it turned out that the console was only connected to one page. We rearranged the pages and our data was successfully collected.
Now that we had our back projection, website, and command and control code working, it was time to combine them. The command and control code would control the radar to collect data, which would then store this data and send into the back projection code to form an image. All of this code ran under the surface. The highest layer was a website we created to accept parameters and display the final image. We implemented this by running the website, as well as the other two parts of the code, on a remote server. We used Linode to host our virtual server. This means that anybody who has access to the internet can go to the website and emulate a radar to form an image. Through integrating these three separate systems, we learned to work together as a team to brainstorm ideas and bring them all together at the end.
Finally, the most important lesson we learned was how to work together as a team to create one final project. While there were a few bumps along the way, such as live share not connecting right, computers not being able to run the files from Git, or platforms that don't support the code we made, we were able to pull through. Though each of us struggled in different areas, our final product was able to accomplish the task at hand, and we felt proud of our work overall.
On the final note, the three of us want to express our gratitude for everyone who made this experience possible. We want to thank the sponsorship for making BWSI so incredible. We appreciate the amazing panelists that took time out of their day to give insightful lessons in the daily seminars. They answered many of our questions regarding college and career paths. Finally, I want to personally thank our instructors, Ramu and Frank, as well as the student assistants for their incredible work in putting together the programs to make this course as rewarding as possible, even in a virtual setting.